G'day Year 12s. For this part of the topic, some of the videos will be in this format where I'm doing it on a recorded PowerPoint rather than on a whiteboard. The reason for that is there is going to be a lot of drawing involved with this part, and it's a bit easier to do it on existing graphs on the PowerPoint. All right, so this whole part of the topic revolves around critical path analysis, and there are a number of aspects of that we'll be looking at in today's video. This video probably will go for a bit of time, but it does cover a lot of the crucial stuff that we need to cover in this part of the topic. All right, so a lot of it revolves around this sort of thing, where we have both activity charts and directed graphs. Now, the directed graphs are the more important aspect of this topic. It's where we're going to be doing the majority of our critical path analysis. So on here, we're just going to go through a few key terms. So make sure you're copying this down. Obviously, pause the video at any time. So directed graph, we've spoken about that a little bit. On the right-hand side here, we have a directed graph. Basically, it's just defined by a network which has edges where there are directions and quantities. So each one of these edges are labeled with both a letter and a number, and they have a very specific direction to them. Typically, they go from left to right. So the nodes or the vertices, they represent the start of it and end of every activity. The more important part here is the edges. They are the activities that are occurring. So in this one here, we have A, which has 4. That's the activity that's occurring at that point. Then coming off that, we have a number of other activities, D, B, G, all the way until we finish with activity F down the end. To the left of the graph, we have what's called the activity chart. So these two things are equivalent. They're just represented differently. A skill that you need to have here is to be able to take that activity chart and convert it into a directed graph, which we'll be doing on the next slide. So here the activities are basically getting up in the morning. We have preparing breakfast, cooking it, eating it, showering, getting dressed, etc. What you have on one column here is what's called the predecessor. So the immediate predecessors are an activity that must occur before another activity can happen. So for example, we have to prepare breakfast. That's a predecessor of cooking it. And then finally we have to cook it before we can eat it, etc. So we have to have some activities occurring before others can happen. And that's just represented on our directed graph on the right-hand side there. So activity A must occur before activities B, D, and G all occur. So we can see that visually in the directed graph there. All right, so here we're going to do a little practice of drawing a directed network that represents the activity chart on the left-hand side here. So step 1 is to look for tasks that do not have immediate predecessors. This is always our starting point. And then look for activities that can start after the first activities and continue from there. As a tip, always work in pencil because often you will need to change connections. All right, so let's start. Let's have a bit of a look. So here, according to this, activity A has no immediate predecessors. So I'm going to start with activity A. Often these will have a value to them as well, but just for the sake of this, we have just edges. All right, so that's taken care of. Next, we have 2 activities which A is its immediate predecessors. So B and C come directly off activity A. So I'm going to add those in. Just like so. You might have drawn it slightly different. This one might be going this way and C might be going straight ahead. It doesn't really matter. It's kind of like your isomorphic graphs. It doesn't really matter the structure too much as long as all the connections are there. Now I can see coming off B, I have got 2 activities that consider B the immediate predecessors, D and E. So I'm going to have D and E coming off mine. Just being as neat as possible. All right, I've drawn them. All right, activity F comes off C. So I'm going to draw F. activity G comes directly off D. And lucky last, H comes off two vertices, E and F. Oh, hang on, what's happened here? My E and F don't connect up. All right, so if this is the case, because H has two immediate predecessors, E and F, it means it needs to be coming off both of them. So what I need to do, this is why I've drawn in pencil, is this one, F, needs to be redrawn so that it connects up with E, so therefore I can draw H directly off that. I'm going to draw it connecting up to the end of G there. Typically, we want these graphs to finish in just one vertex. So when we get to the end, we just draw all final tasks coming into that last vertex. Yours will look a little something like that. Double check, go back through. Do my activities have the appropriate immediate predecessors? If I look at, all right, G, does that have D coming off the back of it? Yes, it does. H, does it have E and F coming off it? Yes, it does. So double check that you've got the correct connections. All right, so here's a lot of the critical definitions, but I'm critical for this particular topic. These are definitely need to be in your notes book somewhere. Most of these will probably make a bit more sense when we do the example on the next slide. So critical path, when we go through a network like we just had a look at before, critical path is a sequence of activities that determine the overall time for a project to be completed in the shortest possible time. These activities cannot be delayed without causing the entire project to be delayed. Earliest start time, that any activity can be started after all prior activities have been completed. So in a moment when we do our example, we'll have those little houses drawn above our vertices where we'll be filling in the earliest starting time and also the latest starting time. As we do it, we're going to do a forward scan, which is the process of looking through a network to calculate the earliest starting time for each activity and the earliest completion time for the whole project. Then we do the opposite. We do a backward scan to determine the critical path of the network. And the lucky last definition here is the float time. It's the difference in time between those paths that cannot be delayed and those that can. So essentially, it's how much time something could be delayed without delaying the entire project. And we have a little bit of a visual and a formula there. There is a bit going on in that picture and in the formula, but the important thing to understand in this diagram is the positioning of what numbers that we need. So have a look at the formula there. You need the latest starting time of Y, which is the next activity you're looking at. So see where that is in the diagram. You need the time that X will take and the earliest starting time of X. So you need those three numbers from your diagram to be able to solve this float time. But we will look at it in the next example. All right, I'm about to move on to the next slide. So if you need to pause it and write those definitions, go for your life. All right, so we're going to look at the same graph that we looked at in the earlier example. So we've got a directed network. A bunch of activities are occurring. We are going to do a full critical path analysis of this, as well as calculating the flow time for a number of the activities. So the instructions start at the first node. So node is just vertex, and add the time of each edge to the earliest start time of that triangle. We write the largest value in the triangle. All right, so when we are doing a forward scan, we are writing in the, say, the roofs of the houses in the triangles. So literally, move from left to right. Each time you encounter one of these houses, we need to fill in its roof. Now, with these, we always start with 0, every single time. So I'm going to write 0 in the roof of this one. All right, now I'm going to move along. All right, activity A, that's occurring. It's taking me 4 minutes. And so 4 minutes have passed. So that's what I'm going to write in this roof. If I'm scanning from left to right, the next house that occurs is this one after D. So we need to write the cumulative total as we run. So 4 minutes have passed for A, now 4 minutes have passed for D, giving us a total of 8 minutes passed. All right, so the next house is where we need to look at all the different options. So we need to look at all the possible paths coming into this vertex. Now what we've looked at so far was A and then D and then E. So that would give a total of 12 if I went from A to D to E. If I went from A to B, my total would be 6. And if I went from A to G, my total would be 5. So if you remember on the previous slide, when we do a forward scan, we write the largest number in the triangle. So the largest occurring there is 12. Moving on to the next one, if I go from where I was to C, that would give me a total of 18. If I went from where I was traveling along H, that would give me a total of 14. So again, my total is the higher value, which is 18. And then there's only one more number coming in, F, which is a value of 2 for a grand total of 20. So that is my earliest completion time for this activity, 20. So I'm going to write that as my answer. So whatever answer you get there, that's your earliest completion time for the project. Now to identify that critical path, this is where we do our backwards scan. So we're going to repeat this process very similarly, but we're going to go backwards. So to start this, we repeat that number in the rectangular part of our house. And as we go through, we're going to subtract numbers. Might change colors for this. All right, so 20 take 2 is 18. All right, so this is where we have two options where we're going backwards. We can either continue there and go across 6 and subtract and get 12, or we can subtract the H and get 16. So based off the notes that we just had a look at on the previous slide, what we do is we go for the larger number. The smaller number, 12. Back up here, there was only one way I could have gone, which was the E, which is 4. So if I subtract that, it's 8. Down here, I've got a few options. I can either go from that 8, subtract the 4, which gives me 4, the 12 take 2, which gives me 10, or the 12 take 1, which gives me 11. Again, we're going with the smallest number, so that's 4. And 4 take 4 equals 0. So you should finish out with 0 in that final rectangle there. If you don't, you've probably done something wrong. So the critical path here is the edges that we have to follow, which makes those highest totals. Where the triangle and the rectangle are the same value. So for this one, the critical path will be A, D, E, C, and F. Those were the edges that made the values in the triangle and rectangle the same. All right, last little thing here is the float time for both of these. Okay, so what we need, first of all, let's look at B. We're going to do this in green. All right, so we've got B here. There's a few things we need. First of all, we need the latest starting time from the house in front of it, which was this 12 here. So that's the value we need. We need the time of the actual activity itself, which is 2. And we need the earliest starting time from the little house beforehand, which is this 4. So for all these float times, those are the values you need. The edge itself, the value in front here, as well as the earliest start time. All right, I just had someone at the door, so I lost my train of thought. Okay, so those are the 3 values that we require. Literally, all we really do is just go from right to left, subtracting as we go. So the float time for B, that latest start time of Y, which was 12. Subtract the time of B, which was 2. Subtract the earliest starting time of the little house beforehand. So B has a float time of 6 minutes. Then G, very much the same. We are going to be using the same later start time ahead and the earlier start time beforehand because these edges are in the same positions. So that one will just be 12 minus 1 minus 4, giving us a float time of 7. Beautiful. Hopefully some of that made sense. You will be doing plenty of these critical path analyses. So if after the first couple you're still struggling, don't stress. Always come back to the meet, ask for help, and keep practicing. Thanks, guys.